Hello and welcome back to our revision series on differentiation. Now in the previous video, what we looked at was what the derivative was and also how to find a derivative from first principles. So this is just a quick summary of what it was. So a derivative, we talked about how it was a rate of change. It describes how two quantities are related to each other, how one changes in relation to another. And the second thing was we talked about the derivative as a gradient function. Now in here I'm going to explain it in a little bit more detail because in this video we're going to go through a few examples where we need to apply that. So with a regular function, so here over here I've written when we have a regular function f of x, the blue function, if we sub in a value x into our function, this gives us what we usually call this is it gives us our y values. So it's usually your y values of a function, or your function values. Of function, let me just call it function. So when we sub in, for example, if we want to know the y value of a particular point, what we do, so let's say if we have y is equal to x squared, that's our function, and we want to find what the value of y is at 1, we sub x is equal to 1 into our function. Now, the gradient function, the derivative, when we sub in values of x into our derivative, this gives us the gradient at x. So when we substitute the x values into our derivative, it tells us how steep the function is at that given point. So steepness at x. So for example, if we differentiated x squared, we get y dash is equal to 2x. And if we subbed x is equal to 1, what that would tell me is at x is equal to 1, the gradient of the tangent is 2, for example, for this case. So that's what we looked at in the last video, and we're going to actually apply this gradient function stuff in this particular video. The second thing was we talked about the derivative as a limit, and we used the process of first principles by taking the limit of f of x plus h over f of x minus f of x over h. So when we did that, we got the derivative, which came from that definition of us trying to get closer and closer to this particular point and get the gradient at that particular point. Now in this video, what we're going to do is we're going to go through a few differentiation rules, because if you remember, we said that we don't want to do this, don't do unless specified. So we don't want to use this first principles method to differentiate unless we are told that we need to do it. So we want to use a different method, and we want to apply a few differentiation rules to actually help us differentiate a whole bunch of different functions. So I'm going to go through all of the rules in this video and go through a few different questions that might be related with answering these particular things. So let's go through these. Now, differentiation rules. Now the first one is our most basic rule, the power rule. So when we've got a power of x, so notice here we've got x and we've got a power n. When we differentiate a power of x, what we do, if you remember, we bring down the power and subtract 1 from the current power. So here, I would bring down the power to the front, so I multiply the whole thing by n times x, and then I subtract 1 from the existing power. So here, it goes to n minus 1. So we multiply by the current power, and we subtract 1. So bring down the power, subtract 1. Okay, so we're going to go through a few examples where we apply this. So in this example, we want to differentiate and find the gradient of the tangent at x is equal to 1. Now, as I talked about with the gradient function, when we differentiate, we find the gradient function. So when we want to find the gradient of a tangent at a particular point, we sub x value into f dash of x, or y dash. So we substitute our x value here. So here in particular, we want to be substituting x is equal to 1 into our derivative to find the gradient of the tangent. So let's have a go at this. So first one here, y is equal to x cubed minus 5x squared plus 2x minus 1. Okay, so like as I said, when we've got a power of x, so notice here we've got a whole bunch of terms, we've got powers of x. What we want to do is we bring down the power, so we multiply, and we subtract 1 from the current power. So what I'm going to do is I'm going to do that from the very beginning. So here I'm going to just use my derivative notation, dy and dx. And so when I bring down the power, this first term, I've got x cubed. I bring down the power. I bring that 3 down to the front. I write x, and I subtract 1 from the existing power. So that 3 now becomes a 2. So I've got 3x squared for my first term. Okay, let's continue that for my second term. Second term, I've got minus 5x squared. Okay, I've got the minus still stays. Okay, I bring down the power like I did in the first one. So here the power is now 2. The power of x is 2, so I'm going to bring that down. 2 times 5x, still the same. And I subtract 1 from that power. So here, when I subtract 1 from the power, I just get 2 minus 1, which is 1. Now, when I'm dealing with algebra, I don't write that 1. If you remember powers of x, I don't write x to the power 1. Plus, okay, final term, 2 to the power x. Now 2 to the power x is just 2 to the power x, 2 times x to the power 1. When I bring that power down, I bring down 1 times 2. I'm not going to bother writing that 1 times 2. I'm just going to get 2. And when I subtract 1 from that power, x to the power 1 minus 1, when I get anything to the power 0, I just get 1. So here I'm just going to get plus 2. Now the final term is a constant term. If you remember with algebra, any term that doesn't have an x or any power of x or any x terms in it is called our constant term. When we differentiate our constant term, it just disappears because there's no power there. So here I'm just going to have this particular part. I'm going to simplify this. So here I just get 3x squared minus 10x plus 2. There we go. So we differentiated by bringing down the power and subtracting 1 from the existing power. Now the second part of this question was we wanted to find the gradient of the tangent when x is equal to 1. What we do when we do that is we substitute x is equal to 1 into our derivative. So here I'm going to write sub x is equal to 1 into my derivative dy on dx. So when I do that, I get the gradient of the tangent at x is equal to 1. So let's do that. dy on dx is equal to 3 times 1 squared minus 10 times 1 plus 2. Here I just get 3 minus 10 plus 2, which gives me minus 5. So to interpret what this actually means, what this would look like is if I was to draw this original function up the top here, this y is equal to x cubed plus 2x minus 1. If I was to graph that, and I found the point when x is equal to 1, so I graph that, I graph it out, and I don't know what it looks like, but I'm just going to take a rough stab. Whoa. What this would tell me is that when x is equal to 1, this particular point, the gradient of the tangent is equal to minus 5. This has a gradient of minus 5. Okay, so that's my first example. I differentiate, I bring down the power, subtract 1 from the power, and if I want to find the gradient of the tangent at any given point, I just subtract the x value of that point. Okay, next example. Here I've got y is equal to 5 over 12 x squared plus 16 over x cubed. Now with this one, the trick that we need to do first is we need to rewrite this using our index laws. Now with our index laws, whenever you've got a power of x in our denominator, it has a negative power. So here, if I was to rewrite this using index laws, this would just become 5 over 12 x to the power minus 2 plus 16 times x to the power minus 3. So that's first step. Usually if the powers aren't in a really nice to read way, like in my first example, what I want to do is rewrite them using my index laws. Okay, now that I've done that, I'm going to differentiate this. So I'm going to use my derivative. I'm going to find the derivative. So I'm going to use my different derivative notation this time, y dash. I'm going to bring down the power, subtract 1 from the power, like I did in the first example. So here, first term, I've got 5 over 12 x to the power minus 2. The power's minus 2. I bring that to the front. I multiply. Negative 2 times 5 over 12 x to the power. Now if I subtract 1 from the power, negative 2 minus 1 becomes minus 3. Okay. Plus, let's do that for the second term. I bring down the power. Negative 3 times 16x to the power negative. When I subtract 1 from this power, it becomes minus 4. Okay, from here I can simplify this a little bit. So I can cancel out this 2 and from that 12, and I get left over 6. So this becomes negative 5 over 6 x to the power minus 3 minus, because of that negative sign, 3 times 16 gives me 48. 48 x to the power minus 4. Now I can rewrite this without the negative powers. So this just becomes equals negative 5 over 6x cubed minus 48 over x to the power 4. Okay, so that's the first part. Second part is I want to find the gradient of the tangent at x is equal to 1. So I'm going to go sub x is equal to 1 into my derivative to find the gradient of the tangent at that point. So here all I'm going to do, y dash is equal to negative 5 over 6 minus 48. I'm going to put that into my calculator. So negative 5 over 6 minus 48, negative 293 over 6. Negative 293 over 6. So what that tells me is at that point when x is equal to 1, the gradient is a negative 293 over 6. So that's what this particular question tells me. So with these questions and any questions where you've got powers of x which aren't immediate to you, rewrite them as powers, as using your index laws if possible. Okay, final example for this section. I've got, this is missing something. This is meant to be a 3 here. I've got the cube root of x squared. Now once again, we need to use our index laws to rewrite this so that it's in a form that is nice for us to see. Now here we've got an x squared inside my cube root, which is really nice. So we've already got an x to the power 2. But when you've got a root, any root, so whenever you see this root, what we want to do is we want to use a fractional index. So if you remember, this just becomes x to the power 2, which is just from inside my bracket. I've got this x squared inside my bracket, which is nice. Over 3, which is from my square root part, or the root part. Okay, so I've got rewritten my function here. We want to differentiate it, so let's do that. So I'm going to go, this time I'm going to use a different notation. So d on dx, 3 square root x squared. So if we're differentiating a term whether you haven't said that this is y is equal to or f of x is equal to, you can just write it using this particular notation. Okay, so we're going to differentiate that. Now we're going to differentiate it by differentiating this index form. Okay, as I said, we bring down the power. We bring down that 2/3. So this just becomes 2 over 3x, and I subtract 1 from that power. I do 2 over 3 minus 1. That just gives me negative 1 over 3. Now if I wrote this without the negative or the fractional index, this just becomes 2 over 3 cube root of x. So as we did in the previous 2 examples, bring down the power, subtract 1 from the current power. Okay, final step is just we wanted to sub x is equal to 1 into my derivative, d on dx. So d on dx, cube root x squared, is equal to 2 over 3 times the cube root of 1, which gives me 2 over 3. So if I was to graph this particular function at x is equal to 1, we have a gradient of 2 over 3, roughly that. Okay, so this is the first rule, the power rule. With these, this is the basic one that we're going to actually apply in all the next examples most of the time. We bring down the power, we subtract 1 from the current power. Okay, so that's the first set of rules. Now the second one is called my chain rule. Now with a chain rule, what we're looking for is a function that's inside a bigger function, a function within a bigger function. So that's what I've actually written here. So if y is equal to f of f, that red part is my big function, and u of x is my inside function. So I'm just going to write that down. So f of f is my outside big function, and my u of x is my inside function. So I've got my outside function and an inside function. So when I differentiate this, what this becomes is I differentiate the outside function. So differentiate the outside function, treating the whole thing as a u. and then I times that by the derivative of the inside function, u dash x. Now sometimes they also write this in a different way. So they also write this as dy on dx using my derivative notation here. We sometimes write that as dy on du, so differentiating my outside function times du on dx. So with the chain rule, what we want to do is we want to differentiate the outside function, and then we want to multiply that by the derivative of the inside function. Outside, inside, and then multiply the two. This is also on your reference sheet. So on your Nessa reference sheet, you have all of these derivative rules that we're going to actually go through today, with the exception of that power rule in a bit. So here, on our Nessa reference sheet, we've got these rules. Now, the chain rule that I've just shown you is this one here. This thing here is that exact same chain rule that I've just shown you. But we've also got another version of this chain rule, which is over here. This one over here. This is a special version, a special case of the chain rule. So this is in particular where we've got a function. So here, if you notice on the left-hand side, so if our original function is f of x to the power n, so we've got a function that is being raised to a power n. Here on the bottom one, our chain rule underneath is for any general function. Any general function. So this is on your Nessa reference sheet under the section, I should have said this at the beginning, under the section on differential calculus. So you don't actually need to remember this. All you need to do is remember where it is and actually how to apply it. So if I'm looking at this, the way I look at it is I go, oh, actually, y is equal to g of u. So I've got g as a function, and I've got u as a separate function where it's f of x. So this is just a function, g of, if I was to write u inside, I've got f of x. So I've got a function f, I've got a function f, which is inside my bigger function g. And so if I do that, I need to differentiate the outside function, which is this first part here, dy on du, differentiate my outside function, then I need to multiply that by the derivative of my inside function, du on dx. And that's what we're going to do in these next examples. So let's have a go at a few examples of this. Now this one, the question is asking us to differentiate and find when the tangent is horizontal. Now if you see the word tangent is horizontal. Now if you remember, the gradient function that we get when we differentiate a function tells us how steep a function is at any given point. If we want the tangent to be horizontal, that just means we have a gradient of 0. So what this means is we need to solve for dy on dx is equal to, our derivative is equal to 0. That's what we're actually looking for. Okay, so let's have a go at a few examples. Okay, first one here. X squared minus 1 all to the power 6. Now we could use that first rule that's up here, fx over n, fx to the power n. I'm just going to use the general chain rule that I've shown you just so that we don't get confused here. Okay, so notice here we've got an inside function and an outside function. Our inside function is this x squared minus 1. That's inside my little brackets here. The outside function is this power 6. So what we're going to do is we're going to treat this whole x squared minus 1 as a letter u. And we're going to, so this whole function, if we were to rewrite this, I'm just going to write this on the side. This is just the same as u to the power 6. So this helps us when we differentiate the outside function part. Okay, so if we were differentiating this, I'm just going to write here, d on dx, x squared minus 1 to the power 6. That's equal to, okay, I'm going to differentiate the outside part. So I'm going to differentiate the bit that I put in the brackets. When I differentiate this, I'm just going to bring the power down and then subtract 1 from the current power. So here, this just becomes 6 times u to the power 5. Bring down the power, subtract 1. Quite simple, just like we were doing in the first part with the power rule. Then I need to multiply that by the derivative of my inside function. Now my inside function is just that u part here. This u part, that's all here. I want to differentiate that part by itself. So when I differentiate that, I do the same power rule. Bring down the power, subtract 1 from the existing power of all the terms in there. Notice here, all I need to really worry about is that x squared term. I'm going to differentiate that part. So that just becomes 2... Oh, I must write this in black. 2x times 2x. Okay, cool. I'm going to simplify this by a bit by dealing with the numbers. So I've got 12x times u to the power 5. Now, if you remember, now this u guy here that I've introduced, this wasn't in my original function. Notice my original question was just this. So I want to get rid of u. So how do I do that? Well, I'm just going to replace u with what I let it represent. So u just represents the whole inside part of my function. So here, this just becomes 12x bracket x squared minus 1 to the power 5. This x squared minus 1 is just my u from up the top here. That's just my u part from here. So that's how we differentiate this function. Now what I need to do now is I want to find when the tangent is equal to 0. So I'm going to solve where 12x x squared minus 1 to the power 5 is equal to 0. Now, in order for us to solve this, we need to factorize it into its factors. Now notice here, I've got 12x. I can't do very much about that on the outside, but the brackets, I can actually factorize this even further. This is just a difference of 2 squares. So this is just x plus 1, x minus 1, all to the power 5 is equal to 0. Okay, I'm going to solve this. So I want to find when each one of my factors is equal to 0. So here, x is equal to 0 means that one of my solutions is x is equal to 0. The second factor here just means that x minus 1 is equal to 0. And my third one, x minus 1, means that x is equal to 1 is a solution. So therefore, gradient is therefore horizontal at x is equal to 0 and plus and minus 1. Okay, so this is how we differentiate using the chain rule. We found what our inside function and our outside functions are. We differentiate them separate. We differentiate them. You can do it separately. If you want to write it out fully, so you see which part, what is your u, and identify what is your u, that might be helpful for you. Once you get used to this and don't need to do that particular step, you don't actually need to write this first. You don't need to necessarily write this step as you don't need to write this step as much. You can just jump to that last one. Okay, so I'm just going to show you another example of this. So here, we've got 25 minus x squared. Okay, so actually, let me just change this one up a bit as well to make it a little bit trickier. Let's make this 25x minus x squared. Okay, notice here, once again, I've got an inside function, 25x minus x squared. And I've got an outside function, which is the square root, which is applying to the whole of that 25x minus x squared. So what I'm going to do first is I'm actually going to rewrite this using index notation. So this guy is just 25x minus x squared to the power. When we've got a root, it's a fraction index. So that tells me this is to the power of a half. Okay, I'm going to differentiate this guy. I'm going to differentiate the outside. Then I'm going to differentiate the inside, and I'm going to multiply the two. Okay, so I'm going to write d on dx square root 25x minus x squared is equal to. I'm going to differentiate the outside function. So I'm going to treat this whole 25x minus x squared as one whole thing. I'm going to bring down that half power, so I'm going to bring that half down. Now, if you need to write that u, this guy is equal to u, you can. I'm just going to show you what I normally do once you start to get the hang of this. So I'm going to write this as half 25x minus x squared. Now when I subtract 1 from that power, I subtract 1 from that half, it goes from half minus 1, which is negative a half. Negative a half. Times, I'm going to differentiate the inside. When I differentiate the inside, I'm just going to get, well, when I differentiate, I bring down the power, subtract 1 from the power. So for that first term, 25x, bring down the power, 1, so I just leave that 25. Subtract 1 from the power, we get the power 0, which is just 1, so I have this, 25. Minus, differentiate x squared, bring down the power, 2x, subtract 1 from the power, we've got a power 1, we don't write that, so we just have this. Okay, so my final answer here, I have a half, 25 minus 2x, 25x minus x squared to the power negative a half. Now I'm going to rewrite this without my indices, so this just becomes 25 minus 2x over 2 square root of 25 minus x. 25x minus x squared. Okay, now I want to figure out when this particular graph is horizontal. So what I want to do is, to find horizontal, I solve dy on dx is equal to 0. So I'm going to solve where the derivative is equal to 0 to figure out where it's horizontal. Okay. When I'm solving that, I'm just going to get 25 minus 2x over 2 square root 25x minus x squared is equal to 0. When I solve this, I'd multiply this by the denominator, which just gets rid of the bottom part. So this just means I have 25 minus 2x is equal to 0. Negative 2x is equal to negative 25. So x is equal to 25 over 2. So this tells me that this particular graph, when I graph it, will have a horizontal point when x is equal to 25 over 2, or 12.5. Okay, so that's my chain rule. When I have a function within a function, I need to use the chain rule. Function within a function within a function means I need to use the chain rule. So I differentiate the inside function, differentiate the outside function, and multiply the two together. Okay, second differentiation rule down. 2 more to go. Third one is my product rule. Now, if I have two functions that are multiplying together, so here the notation that they've used for that is my first function. They've written it as u of x, and my second function is v of x. Okay, so when we've got two functions that are multiplying together, so here, if you remember with algebra, we've got hidden multiplication symbol. If I've got two functions that are multiplying together, what I need to do is I need to apply the following rule. So how it's usually written is u dash of x. So I differentiate u, my first function, and times it with the original v function. And then I need to add on top of that the original u function times the derivative of the second function v. So that's what the dashes tell us. So we differentiate one and we multiply by the original function of the other, and then we add the original function of the first one that we differentiated times the derivative of the second function that we haven't differentiated yet. Now, often this isn't written in this particular form. The shorthand and the short way to remember this is u dash v plus u v dash. So that is the formula that we're going to use. Now, this is also on our reference sheet. So if you have a look at the Nessa reference sheet, same section in differential calculus, we have this particular product rule over here. This one's my product rule. So notice here, it's very similarly written. So we've got a function. Our u function is just, y function is made up of two functions, u and v. And here, how they've written it is a little bit different to the way I've written it in the way above. So if you notice, we've got the original function u, and we're timesing it by the derivative dv on dx. So dv on dx is just a notation for our derivative, if you remember from our previous examples. So here, u times the derivative of v, plus v times the derivative of u, du on dx. So that is this particular case here. So with this particular rule, and the same with the next rule, if you remember in class we used a particular method where we identified u, identified v, we differentiated the two of them, and we drew arrows between the two to remind us which ones we need to add together, multiply together, and then we added the result. So that's what I'm going to do underneath here. So what we want to do is we want to differentiate and write the result in fully factored form, and find the gradient of the tangent at the given point. So here the additional step that we want to do is find the gradient of the tangent at a given point. Now, just like in the first example that we did with the power rule, to find the gradient at any given point, we sub in the x value. So if we get given a point with coordinate xy, all we want to do is substitute the x coordinate. We substitute the x coordinate of our particular point. So that's how we find the gradient of the tangent at any given point. So let's have a look at these examples. First one, we've got x times x minus 10 to the power 4, and we want to find the gradient at the point 1, 1. So here, we want to find the gradient at the point 1, 1. We're just going to, for this example, we're going to sub x equal 1. So before we do that, we need to differentiate. Now with this particular example, you might be tempted to go, oh, I can just multiply x into my brackets. Do not do that. That is incorrect. You will not get, that is not the correct expansion for this. You can't just multiply x into your brackets. What we need to do is we need to use a product rule. Notice here, we've got x times x minus 10 to the power 4. We've got a product here. The two functions multiplying together. So what we need to do, I'm going to name the two functions. I'm going to call my x my u function, and my x minus 10 to the power 4 as my v function. So that's what I'm going to do underneath. I'm going to just write u is equal to x, and v is equal to x minus 10 to the power 4. Okay, I'm going to differentiate the both of them. So here when I differentiate x, I just get 1 using my power rule. Here for my second one, notice we've got a function within a function. So we need to apply the chain rule that we just went over in the previous example. When we differentiate, we first differentiate the outside function. So here I'm going to differentiate, bring the 4 down, 4 bracket x minus 10 to the power 3. Then we need to multiply that whole thing by the derivative of the inside function. Luckily for us, when we the derivative of the inside function, it's just 1. So we don't need to do very much there. Now in class when we went through this method, what we did was we drew arrows between the opposing functions, so the original function and the derivative of the other one. And so this tells me that I need to multiply those two together. So here, when I want to find the derivative, I'm just going to write dy on dx is equal to, I'm just going to use the rule that we have identified. So I'm going to connect u and v dash. So here, I'm just going to go x times 4 x minus 10 to the power 3. So that's this first arrow going from x to 4 times x minus 10 to the power 3. Plus the other arrow, 1 times x minus 10 to the power 4. So once we've done that, we're just going to simplify this a bit. So this becomes 4x, x minus 10 to the power 3, plus x minus 10 to the power 4. Okay, we've used our product rule and written it like this. Now, with the product rule, often what you can do is you can actually factorize out a common term from both of your terms that you're adding together. So notice here, I've got both terms actually have this x minus 10 factor, but we've got different powers of it. So we need to take the smallest power possible. For us, that is x minus 10 to the power 3. So I'm going to factorize out x minus 10 to the power 3. So I'm going to have x minus 10 to the power 3, bracket. For my first term, what I'm left over with is this 4x. I'm going to write 4x plus, in the second term, when I take out x minus 10 to the power 3, we've got another x minus 10, because here we've got a power 4. And so this is plus x minus 10. Okay, I'm going to simplify my brackets. So here this just becomes x minus 10 to the power 3, 5x minus 10. We can further factorize the second bracket. We can take out 5. So here in fully factored out form, this just becomes x minus 10 to the power 3 times x minus 2. Now the second part of this question was we wanted to find the derivative at p, which was the point 1, 1. Now for the point 1, 1, as it turns out, the point 1, 1 isn't actually on this particular function, which is a little awkward. But if we're trying to find the gradient at any particular point, we just sub in the x value at that point. So here I'm going to sub x is equal to 1 into my derivative. So let's do that. dy on dx is equal to 5 times 1 minus 10 to the power 3 times 1 minus 2. Now, if I put this in my calculator, whoop, that's not the right thing. This becomes, so, let me try this. Clear this. 5 times 1 minus 10 to the power 3 is, I'm going to put some brackets here, negative 9 to the power 3 times minus 1. So this gives me 3,645, which tells me at x is equal to 1, we have a gradient of 3,643. So it's a really steep positive tangent. Okay, that's my first example. So here with our product rule, we need to identify our two different products of two functions which are multiplying together, and then apply the product rule. Okay, second example. Here we've got two functions that are multiplying together, so we're going to do the exact same thing. Let's identify the parts of my function. So here, first one, let's call this one u. So x cubed plus 5x. So u is equal to x cubed plus 5x. My second function is v, which is the second one, 3x plus 2 squared. 3x plus 2 squared. Okay, so let's use our product rule. So here, u dash. We're gonna find the derivative of each of my functions here. So u dash is just equal to 3x squared plus 5 by using my power rule. Second one, because it is a function within a function, we need to use the chain rule. So we're going to differentiate the outside of the function. So I'll bring down the 2, 3x plus 2 to the power, that's to a power 1 now, times the derivative of the inside, which is just 3, which gives me 6, 3x plus 2. Okay, with our product rule, we're going to connect our opposites and then multiply them together and then add. So let's do that. So here, d on dx of my original function, x cubed plus 5x times 3x plus 2 squared is equal to the original function of my first one, so x cubed plus 5x times the derivative of my second one, times 6 bracket 3x plus 2. Okay, and that's plus 3x squared plus 5 times 3x plus 2 squared. Okay, I'm going to simplify this a bit and write these with the terms in the spots. So here, this becomes, for the first one, we can bring that 6 to the front. I'm going to also factorize out this first term here. So notice I've got x cubed plus 5x. I can take out an x from there. So what I'm left with is x squared plus 5 times, I've still got this 3x plus 2 from the second term. Okay, so that's my first term, plus 3x squared plus 5 times 3x plus 2 square. Okay. So, once we've done that, what we can do is we can try to factorize this fully. So we can take out any common factors. So notice here, let me just check that I've done this correctly. Yes, I think I have. Cool. Okay, I'm going to take out common term. For us, the common term for this one, I believe, is this. Yep. Okay, my common term, I think, is this 3x plus 2. So I've got 3x plus 2. I'm going to take that out from both terms. So I got 3x plus 2. First term just becomes 6x times x squared plus 5 plus 3x squared plus 5 times 3x plus 2. Okay, so there we go. I have factorized out my 3x plus 2, and I've gotten this. Okay, let's expand this and simplify the stuff inside my brackets. This is where it gets a little bit longer and trickier. So this is where your working out needs to be a little bit neat so you can actually see where everything is. Okay, I'm going to expand out that first part here. This just becomes 6x cubed plus 30x plus, I'm going to expand out the second bit. So here, I'm going to use my FOIL method. So this becomes 9x cubed plus 6x squared plus 15x plus 7. Whew, okay. From there, we can take out we can start to combine terms with the same x power. So here, notice here we've got 6x cubed and 9x cubed. So this becomes 15x cubed plus 6x squared plus 45x plus 7. Yep, there we go. Okay, cool. There we are. Okay, now we have this in fully factorized form. Okay, now once we've done that, what we want to do is we want to find the tangent at the point p is equal to p52. Now, p52, I just need to substitute the x value at that particular point. So here, I'm just going to go sub x is equal to 5. Okay, so this is where it gets a bit long. Okay, sub x is equal to 5, so my derivative d on dx is equal to 15 plus 2 outside of, oh gosh, this is going to be a big number, times 5 cubed plus 6 times 5 squared plus 45 times 5 plus 7. Okay, let's put that in my calculator. This becomes 50. Oh, the first part, it just becomes 17 times bracket 15 times 5 cubed plus 6 times 5 squared plus 45 times 5 plus 7, 38,369. So there we go. That's how we find the gradient of the tangent at that particular point. Okay, so product rule. What we want to do is we want to identify our two products in our function. Two products that make up our original function. Differentiate both of them, then connect the opposite ones, and then multiply those together, and then subtract, and then add them together. Okay, cool. That is our product rule. Final part. Final rule is our quotient rule. Now, the product rule is when we have two functions multiplying together. The quotient rule is we have two functions dividing each other. So here we've written them as a fraction, u of x over v of x. So if we have that particular rule, if we have this particular thing happening, what we get is v dash x times ux. This time it's minus u dash x times vx over vx squared. So here, this is the quotient rule. If we have two functions that are dividing each other, we apply this particular rule. Alternatively, the way that it's also sometimes written, the shorthand is just v dash u minus u dash v over v squared. Okay, so like we did in the previous example, what we need to do is actually find what u and v are, differentiate them, and then put them into the relevant spots here. Okay, just like I said with my product rule, this is also on our reference sheet. So it's this last one over here, which looks really, really messy. So here, this is your quotient rule. So with our quotient rule, what we have is we've got v. Oh, hang on, I've actually written the wrong way around here. My bad. Whoop. This should be, and sometimes this is why I forget it, and so the reference sheet is going to be quite helpful. Dash, it should be here. So it's vu dash minus uv dash. I knew something was wrong. Okay, so here they've written it. V times the derivative of u. So here the derivative of u minus u times the derivative of v. Okay, so what we want to do is identify what our u function is and our v function is, and then apply it into this rule. Okay, so first one here, we've got this function y is equal to 2x plus 1 over 2x minus 1. So using our quotient rule, what we're going to do is we're going to identify what u is. U is always the numerator, v is always the denominator. So here I'm just going to write u is our numerator, 2x plus 1. So I differentiate that, so I get u dash is equal to 2. V is always the denominator, so that is always going to be, that's just going to be 2x minus 1. So v dash is just going to also equal to 2. Okay, now that I've done that, I'm going to apply my product rule, my quotient rule. So dy on dx is equal to, okay, so u dash v. So u dash is this first part here. So that's just going to be 2 times 2x minus 1 minus v dash u. So v dash u, 2 times 2x plus 1 over v squared. So v is just this part over here, this second, the denominator function. I'm just going to square that, 2x minus 1 squared. Okay, now that I've done that, I'm going to expand out the terms in the numerator and simplify it. So here, this becomes 4x minus 2 minus 4x minus 2 over 2x minus 1 squared. Now if you have a look, we've got a 4x minus and a minus 4x, so these two terms are going to cancel out in my numerator. So that leaves me with minus 2, which is negative 4 over 2x minus 1 squared. So there we go. That's how we use our quotient rule. We identify our u and our v. So u is our numerator, v is my denominator, and I differentiate them and then plug it into my quotient rule. So check out your quotient rule on your reference sheet if you forget which parts go where. Even I forgot it early in this video. So that's use your reference sheet. Okay, next and final example of this video. Here I've got this particular function y is equal to this guy here. So I'm going to identify u and v. So u is equal to 3x plus 4 to the power 5, and v is equal to 2x minus 5 to the power 3. My numerator and my denominator. All I need to do now is I go u dash is equal to, now notice here this requires me to use a chain rule. I've got a function within my function. So 3x plus 4 inside to the power 5. That power 5. So I'm going to differentiate the outside. So bring down that 5. 3x plus 4 to the power 4. I'm going to times that by the derivative of my inside function, which is just 3. So I've got 15, 3x plus 4 to the power 4. I'm going to do the same thing for my v. So v dash is equal to, chain rule once again, differentiate the outside function, 3, 2x minus 5 to the power 2, times the derivative of the inside, which is just 2, which gives me 6, 2x minus 5 squared. Okay. Now that I've done that, I'm going to apply my chain rule, or my quotient rule. Why do I keep saying chain rule? Here, u times v dash. So u times v dash. Okay, so I'm going to get 3x plus 4 to the power 5 times 6 2x minus 5 squared. Minus v times u dash, this part here. 15 3x plus 4 to the power 4 times 2x minus 5 cubed over v squared, which is my denominator function squared. So this gives me 2x minus 5 to the power 3, and I'm squaring that guy. Okay, I'm going to simplify the top. So here this gets me 6, 3x plus 4 to the power 5, 2x minus 5 to the power 2, minus 15, 3x plus 4 to the power 4, 2x minus 5 to the power 3. Okay, now that I've done that, I can actually factor, and I've got my bottom part, whoops, I forgot about that. This is going to be 2x minus 5 to the power of 6 using my index laws. Now that I've got that, notice at the top, I can actually factorize out a few common terms. So, notice in both of my terms, I've got 3x plus 4, but we've got different powers of it, 3x plus 4. And we've also got this 2x minus 5, 2x minus 5. So I can take out a common term. So here we just take the smallest power of each one of those. So this gives me, and also we've got a 6 and a 5, which means I can common factor there of 3 as well. So I'm going to take out 3x plus 4. Now the lowest power is a 4, so I'm going to take out power 4 times 2x minus 5. The lowest power of that is square. So what am I left with? From the first term, when I take out all of this guy here, I'm left with, at the front, I'm going to have a 2 instead of that 6 because I've taken out 3, times 3x plus 4 to the power 1 because I've taken out 3x plus 4 to the power 4. Okay, for my second term, I'll be left with minus 5, 2x minus 5 over 2x minus 5 to the power 6. Okay, I can simplify this further. Now notice at my top and the bottom, I've also got this 2x minus 5 term, so I can cancel out a few of these. So I can cancel out this guy, and I'll be left with power 4 down here. So here I'm going to have 3x plus 4 to the power 4. I'm going to deal with the guys inside my bracket, so I'm going to expand it out. 6x plus 8 minus 10x plus 25 over 2x minus 5 to the power 4. Ooh, okay, almost there. 3x plus 4 to the power 4. I'm going to simplify what's inside my brackets, so I get minus 4x plus 33 over 2x minus 5 to the power 4. Now, just in general with your terms, I usually don't want to have a negative sign in front of any of my x's, so I'm going to take out the negative to the front. So I get negative 3x plus 4 to the power 4, 4x minus 33 over 2x minus 5 to the power 4. Okay, so there we go. There's my quotient rule. Now notice these are actually quite long, so you want to actually be really careful with your working out, just so you identify where u and v are and make sure that you don't miss out any terms. So with that, you should be able to do a few of the questions in the revision booklet. All the best. Good luck with that. If you have any questions, feel free to ask.